Okay, welcome to topic 5. Today we're going to be talking about gears and rolling contact and how they relate to mechanisms. Okay, so here is the reading assignment. This is actually pretty useful, at least just to skim, so I'd recommend it, but again, you don't need to know it. This should give you everything you need. Okay. So let's start with the simplest gears, spur gears. Okay, so these are spur gears. They're the most famous gears. They call the small one the pinion and the large one the gear or wheel. Okay, and together they make a gear set. Now, first of all, what's the point of gears? Oftentimes in mechanisms, you want to be able to convert a continuous rotation of one speed into a different rotation on, a different continuous rotation on a different shaft. Okay, so that's exactly what gears do. They're basically transmission elements that convert speeds to different speeds along different shafts. Okay, and you recall when we drew our mechanism skeleton diagrams. Of course, engineers don't want to draw all the teeth on the gears, so they just draw circles. Except, if you think about it, the question is, well, which circle is it? Is it the circle of the outside of the teeth, the inside of the teeth, somewhere in between? The answer is it's a circle somewhere in between, and it's called the pitch circle. Okay, it's a very specific circle, and it has a radius r. And anytime you see a skeleton diagram of gears, you can just assume that is the pitch circle's radius that's shown and that's drawn, because it doesn't make sense to draw any other kind of circle when you're talking about a gear set. Okay, so you're probably asking, well, what is the pitch circle? Well, it's actually a little tricky, so it's going to take a little bit in the lecture to explain what it is. But it's basically the master circle off of which all calculations are based. Okay. All right, so if we zoom in, okay, the circle on the top land, so the outermost part of the gear, you can see the top land there, is called the Addendum Circle. You got to memorize that. And then there's, of course, a bottom land where the tooth bottoms out, and this very bottom one is called the dedendum circle. Okay, and the pitch circle is a circle somewhere in between. You can see I've drawn it here in red. That's a portion, a sector of that the pitch circle's circumference, and it is always between the addendum and dedendum. But you might think, well, is it halfway? Is it the average? You know, what is it? Well, it's neither of those. It's just somewhere in between, and I'll teach you how to find it. Okay. All right. So. Let me introduce the concept of a diametral pitch, okay, usually shown as capital P as a scalar looking term, italicized, okay, and it's defined as the number of teeth on a gear divided by 2 times the pitch circle's radius. Okay, and so far we still don't quite know what the pitch circle is, except it's some circle between the addendum and dedendum circle, and it's the master circle off of which everything's calculated. So we have this new equation, and this is kind of a characteristic number for a gear, but what does it mean? Well, honestly, it doesn't have much physical meaning, but the circular pitch, small p, italicized usually, so you got a capital P italicized diametral pitch. You want to memorize that, it's this, and small p italicized is the circular pitch. It is a function of the diametral pitch, so it's pi divided by the diametral pitch. That's all it is. Okay, and that one does have physical meaning. So if you take pi and you divide it by this, you end up getting 2r pi, which you might recall is the circumference of the perimeter of a circle. Okay. Divided by the number of teeth on the gear. Okay, so you could imagine if you take the whole circumference of the pitch circle and you divide it by the number of teeth, then that will tell you how much the teeth are spaced out from one edge of the pitch circle to the next one. Okay, it's also, you could draw that line right in the middle of the tooth, and it would be the same distance in the middle of the tooth, basically the distance along that pitch circle. Okay, so it's basically, so the circular pitch does have a practical meaning. It's the distance from one tooth to the adjacent tooth measured along the pitch circle, and it's a function of the diametral pitch according to pi divided by the diametral pitch. And remember, diametral pitch doesn't have much physical meaning, but you can kind of think of it similar to circular pitch. Okay? So by the way, yep, there's the circular pitch distance. Okay. So a couple other definitions. You know what the addendum circle is? Well, the addendum A is the distance between the pitch circle and the addendum circle here. So it's that distance, so that's A. And D is the dedendum, and it's the radial distance from the pitch circle to the bottom of the land of each tooth. So this is the D or the dedendum. Okay? So those are useful to know, and don't get them confused. So a lot of people think addendum and dedendum is the radius or diameter or something of the addendum and dedendum circle. That's not correct. It's the radial distance from the pitch circle to the addendum or dedendum circle. Okay? And note that the pitch circle is not necessarily halfway between the top and bottom land. So A and D don't usually equal each other. Okay, it's a little more complicated than that. But we'll answer, how do you find the pitch circle of a gear set? By the way, you can't, if I just hand you a gear, you can't tell me what its pitch circle is. It doesn't exist except in the context of a gear set. Okay, so that gives you a hint into the complexity of how you find it. Okay, but it's frustrating because it's the most useful circle and it's what you always draw. Okay, so, all right. But anyway, I promise you'll understand it shortly. Okay, so let's look at the fundamental law of gearing now. Okay, let's do a review of instant centers here from topic 3. Okay, you've got two bodies labeled 2 and 3. And body 1 is the ground. Okay, so you've got 3 bodies. And ask you the simple question, where is the instant center of link 1 and 2? Well, it's right there. That's P12 or P21, right? That's where they both have the same velocity, which is a velocity of 0 because the ground is fixed. Okay, okay, where is the instant center of link 1 and 3? Well, same thing. It's right there. P13 or P31. Either one you can say is correct. Okay? All right, and now the question is, where's the instant center of links 2 and 3? In other words, as you imagine these in this instant, can you imagine where both bodies have the same velocity? Well, that's much trickier to do. So I recommend you use the Arnold-Kennedy theorem. And if you recall, the Arnold-Kennedy theorem says if you have any 3 bodies you're comparing, which is exactly how many bodies we are comparing here, the instant center of the instant center of all 3 pairs of bodies lies along this common line, which, by the way, is called the line of centers because it connects the 2 centers, the pin joints of these 2 rotating bodies, which are, arbitrarily shaped gears, say. So it's the line that connects the 2 centers of the gear, so it's the line of centers, okay? Okay, so P23 lies somewhere on this dashed line, the line of centers. And what else do you know? Well, you see this joint here, and by the way, that's got to be rolling and slip. If it was rolling only, right, then the system would be locked up, right? But it's rolling and slip, okay? And so because of that, if you recall from topic 3, you don't exactly know where the instant center is between these 2, but from that joint, you know it lies somewhere along the normal line shown here. Okay, that line right there is guaranteed because it's rolling and sliding. You know that it lies somewhere along that line. Well, if you know it lies somewhere along the line of centers, you know it lies somewhere along this line of action, it's called, which is the line where the force from one of the bodies acts on the force of the other, or there's like a pressure along this line, okay? Well, then you know the instant center between these two is where they intersect, okay? So there it is. P23 is at this point P, okay? All right. Thus, because we know from Arnold Kennedy and from deduction that that is the instant center between bodies 2 and 3, we also know that's where they both have the same velocity. So if this was a point P on link 2, you know that velocity would be the same as if it was a point on link 3. Okay, so you can calculate this equation from that. You know omega 2 times R2, okay, is going to be the velocity of point P. Remember, the velocity there is 0 of O2. And you use the velocity difference equation to march from there to that point as if it were on 2. And it's omega 2 R2 as a scalar, okay? And you know that the velocity, if that were a point on this body, you could do the velocity difference equation. The velocity here is 0, and it would be omega 3 R3, where, right, R3 is the distance from there to that point. You can see it's swept out there, labeled R3 and R2, okay? So you can see those guys equal because it's the instant center. By definition, they're the same velocity. Okay? So if you rearrange this equation, then that tells you the ratio of output speed, angular speed, to input speed. If you had a motor attached to 2, and you're rotating a constant angular velocity omega 2, then if you times that by this ratio, it would tell you what omega 3 is, right? Well, it's interesting. We find from this equation that ratio is R2 divided by R3. Okay? So, by the way, P23 is often called the pitch point P, another P. Okay? And the question is, will this pitch point move as links 2 and 3 rotate? Okay? The answer is, well, I want you to think about it first of all, but you can put me on pause. But anyway, assuming you take me off pause here, the answer is it will rotate, or it will move. Okay, so you can imagine as this sweeps to a different position and this rocks back, and assuming they're still touching, right? You could imagine, even though the line of centers isn't going to move, that's fixed there. That normal between those two surfaces, that line, this black, the line of action, will move. It'll wobble at different angular positions of omega 2, and as a consequence, P will move up and down this line of centers depending on the position, and therefore the ratio of R2 to R3, the distance between these two, will vary, and consequently so will the angular velocity ratio. Okay? Okay, and this is not necessarily desired, okay, because usually, right, the whole purpose of gears is you really want, if you've got some constant input angular velocity on one shaft, say omega 2, and usually you want to convert that into some constant angular velocity about another shaft. In this case, it would be O3. But because the pitch point is going to move, and because the ratio R2 to R3 and omega 3 to omega 2 is going to change, then if you put a constant angular velocity into 2, you're going to get a changing angular velocity of 3. And that will violate what's called the fundamental law of gearing. Okay? So the fundamental law of gearing states that as gears are going through their mesh, or as gears are conjugate, so by the way, going through their mesh means they're, here's their mesh, they're going through their teeth. As they're going through their mesh, their pitch point must remain stationary on the line of centers so that the speed ratio remains constant, okay? So if gears do that, that's when they're conjugate. That's another term that you can memorize, okay? And, as long as they're conjugate, as the teeth are going through their mesh, that means their pitch point remains the same, and that means their ratios don't change, and so the angular velocity ratio maintains constant, independent of the angular position of the input or the output, and consequently, you obey the fundamental law of gearing. Okay? This also means that the gear set's first order kinematic coefficient must remain constant. Okay, so if the fundamental law of gearing is true or is held fixed, or is satisfied, is the right way to say it, then the first order kinematic coefficient, which remember is the derivative of the output with respect to the input gear. Okay, so if the link 2 is the input and link 3 is the output, those have to stay the same. And we can prove this because you know the ratio of these is the ratio of omega 3 over omega 2, because omega 3 is d theta 3 divided by dt, and omega 2 is d theta 2 divided by dt, and the dt's will cancel, right? And then you know from what we just proved on the last page that that's this ratio, okay? So as long as the first order kinematic coefficient is constant, that means those ratios will be constant, and that means we're obeying the fundamental law of gearing and the gears are conjugate, okay? Okay. Note that if two gears with triangle-shaped teeth were mated and the angular velocity of the input gear is constant, the angular velocity of the output gear would accelerate and decelerate cyclically. Okay, this is because the teeth push on each other. As they push on each other, they cause the pitch point of the two gears to change along the gears set's line of center. So you could imagine, if you just put these two gears together with triangular teeth, as this one rotates with a constant angular velocity, because the teeth are so bizarrely geometrically shaped, you would find the output gear would speed up, slow down in a cyclic way, and you would violate the fundamental law of gearing. So, this begs the question, what is the ideal tooth shape to achieve the fundamental law of gearing? Because a lot of people that don't know anything about gears, particularly, a lot of artists will draw gears in logos and stuff of companies, and it drives me absolutely crazy that sometimes they use triangles, sometimes they use squares, and they'll use these arbitrary teeth shape, and in the very logo of their company, they're demonstrating they have no idea how mechanical things work, because pretty much every shape I've ever seen an artist do would violate the fundamental law of gearing, and even though it would convert an angular velocity to some output, that output is going to be fluctuating in speed instead of maintaining the nice constant speed that gears are intended to do. Okay, so it turns out there's really only one tooth shape, okay, that obeys the fundamental law of gearing, and the answer is it's an involute tooth. Okay. Okay, and so we're going to talk about that. So how do you draw an involute tooth profile so that you can obey the fundamental law of gearing? Okay. Okay, involute gear teeth obey the fundamental law of gearing. That's what they do. Okay, so to generate their profile, what you do is you imagine you have some circle, which is called a base circle. That's another. So we've introduced the concept of a pitch circle. The gear sets have. Well, every gear has a base circle if it's designed correctly anyway, and has involute teeth. Okay. And the base circle is the circle from which you generate the involute profile that obeys the fundamental law of gearing. Okay, so here's how you generate it kind of physically. Okay, of course there's a mathematical equation for it, and this is a good reason to look in the book or just Google it or something. You can find the mathematical equation for involute profiles, but I want you to understand the physical way you can get them. If you wrap a string around the base circle and you pin it here, and then you pull it taut and put, say, like a pin in the string here, as you lift your hand up and down, wrapping it around the drum here of this circle, the pen will trace out an involute profile. Okay? And this is the profile on the edge of teeth that will obey the fundamental law of gearing. Okay? Okay. Couple things about this involute profile. The particular contour of the involute tooth profile is a direct function of the radius of the base circle from which they were generated. Okay, so if you look up the mathematical equation, this profile is very much a function of this base circle radius. You can imagine as the radius gets smaller, if the gear's base circle radius is smaller, then you could imagine as you pull that string around its base, the involute profile will be more curvy, and it'll still count as an involute profile, of course. So there's not just one involute profile. It's the kind of profile that's, of course, based on the base circle, right? And then if you can imagine, as the radius of the base circle gets larger and larger and larger, that involute profile gets less and less curvature, okay? Until finally, by the way, if the radius of this became infinitely large, if the base circle is infinitely large, so it's actually a flat plane instead of a circle, then that involute profile would be a straight line, okay? So involute profiles can be straight lines on, say, a rack and pinion, which we'll talk about later, okay? Okay, but one important thing to note that is kind of the key to deriving this for the involute profile as a function of the base circle radius is that the length of the string from the base circle to the tracing point, okay, so from this point here where it's tangent to that, wanted to find the curvature at that point along this profile, I draw a circle and its center would be there and its radius of curvature would be there. So from that little insight you could probably mathematically deduce what that is and back derive it. Okay, the other thing is note also that the involute contour only exists outside the base circle. So you can't, of course, you can't physically pull the string through the base to generate a curve below this line. And it mathematically doesn't exist except outside of this circle, the base circle, okay? And by the way, if I just handed you a gear, the way you could find the base circle, you can't just look at it and know where the base circle is. You'd have to reverse engineer and measure what that involute profile is of all the teeth, and then deduce back out what the radius of the base circle is. But of course no one would ever actually have to do that, and it would be a useless thing. But just so you know, if I gave you a gear and it had it has a specific involute profile, if it's designed correctly, that's directly linked to its base circle radius, okay? All right. So okay, so consider these two gears, and these ones are very nicely drawn. They're clearly involute teeth. They have an involute contour, and you can see their line of centers is the red line here connecting O2, the input, to O3, okay? Okay, and you can see because they're involute, they are conjugate gears, and they're obeying the fundamental law of gearing. In that you can see that they have the same angular velocity, and it's not that they have the same angular velocity, although they happen to, but because they're they both have a constant angular velocity. As this remains constant, that one is constant. Again, nothing with the fundamental law of gearing says they have to be the same. They just both remain constant. Okay, the ratio stays constant. Okay. So, a couple facts here. So this is the line of center. So every time, wherever the teeth first meet is called point C. Okay? So you can kind of see here, I'm going to follow one of these things. You can see right there's where it touches. And it goes from point C along this line of action, or the pressure line, okay, all the way up here till point D where they release. Okay, so it's kind of hard to see, so we can follow it. We're going to start here and contact all the way at their release. Okay, so C is where they first touch, D is where they release, and you'll notice that the line of action, okay, points in the same direction. So we're talking the black line from C to D points in the same direction regardless of the gear's angular position. So no matter where theta 2 is, however you position this, that line of action is always staying constant and the same. Okay? And where it intersects the line of centers, this red line, is P, or the pitch point. Okay? Right? Because remember, if you're finding the instant center of 2 and 3 at any point, if I froze this frame, at any instant, if you wanted to find the instant center, well, you know it would lie on this red line, and you know it would, wherever these guys first touch, because they're rolling and sliding on the teeth, right, then you know the instant center has to lie on this black line, and of course, if you know it lies on the red line and the black line, then you know its instant center is here at this P. So that's where a point on 3 and a point on 2 would have the same velocity. Okay, is P that pitch point? Okay, so, and because this line doesn't move, P stays the same, and therefore the fundamental law of gearing is obeyed, right? Okay, note also that the line of action is always normal to the interface of the mating teeth, and that the contours of the mating teeth are always tangent to one another. So that's another, these two are true because they're involute. So anytime you have involute teeth, as they go through their mesh here, they remain conjugate for any position, and that essentially means, right, that the line of action is always normal to their two, mating surfaces, which is always the case for rolling sliding joints, right? The line along which their instant center would lie, and that their bodies are always tangent to each other. Okay, the contours of the mating teeth are always tangent to one another. Okay, and so as a consequence, because they're involute teeth, because there are these involute contours, that means that at every position, this line is going to stay steady. It's not going to be wobbling up and down and changing the pitch point along the line of centers. Therefore, that'll stay the same. Therefore, the distance between O3 and P and O2 and P will stay the same. And therefore, the ratio will stay the same. And that means the angular velocity ratio will be constant, and the fundamental law of gearing is obeyed. Okay? Okay, so the contour of the teeth is everything to obey the fundamental law of gearing. It's got to be involute. Okay, note that the only angular position of the gears where rolling occurs solely without slip is when they are positioned such that their point of contact is coincident with the pitch point P. Okay? So, well, let's see. Yeah, so usually when you think of gears, certainly when you do a skeleton diagram and you see two circles, which remember are the pitch circles of the gear, which we haven't, we're almost there. We're close to defining what those are. But those pitch circles, you assume because they're gears that it's rolling contact only. Okay, and that's obviously true, because if you have two gears and you shear them, if you allow the two circles to slide past each other with different velocities in the tangent direction, or the tangential direction, it can't do that because the teeth would shear off. So obviously two mating gears are assumed to be rolling contact only. The truth is, though, and by the way, that means they're a single degree of freedom joint. That means they would be a J1 joint, because they're rolling only. If it was rolling and sliding, it would be a J2 joint. Okay, from harkening back to topic 1, and of course, gears are, just to kind of review, are they higher or lower pairs? Well, they're obviously higher pairs, because at every instant they only touch at a single point or line. If you think of these extruded, right? So that the gear only, one pair of gear teeth, one tooth from each gear is ever engaged, and pushing along this line of action. And where they push, there's a line extruded into the page where they're touching. So since it's not surface contact, it's a higher pair. Okay, but getting to this point, there's a very roundabout way to say, in reality, even though we always model gears as a J1 rolling contact only, the truth is, as their teeth go through the mesh, where they touch, they're actually sliding and rolling along each other from C to P, and then from P to D. But at P proper, right at that point, that's the only point where they really are pure rolling. So